Okay, so the next part we're going to be going over is dynamics and forces mainly. So the idea of a force is really central to what mechanics are and how everything works in our scale of world. And it's not really been clear throughout history. So, like for instance, Aristotle would have thought of forces as kind of what we think of momentum, but it was really Newton who kind of solidified what a force is, and that's the definition that we go off of now. So when we think of a force, we think of anything that acts on a body to either initiate or to stop motion. So when Newton developed his law of inertia, where inertia is a body's ability to resist motion. So when Newton developed his idea of his law of inertia, rather, he said that a body that is at rest will tend to stay at rest, and a body at motion will tend to stay in motion unless acted upon by some outside force. And it was Newton that gave us the famous equation F equals ma, where the force and the acceleration are both still vectors because we act a force with magnitude and it's moving in a certain direction. We push a ball, or we can throw a ball, or gravity being acted upon in like the downward direction. These are all forces that we contribute or attribute direction to. But he wrote it down in a slightly different way. He would have said that a force is the time derivative of momentum, or this. So this is how he would have wrote it. It means the exact same thing, and momentum is something that we'll use a lot later on in the course, but not really as much now. So I think if we look into a few examples first, that's kind of the key of what we need to really try at. But remembering this as the key idea of mechanics or of forces and dynamics. So if we think of a particle moving in three-dimensional space without any forces acting upon it. So that means we have the force vector equaling the zero vector, or just zero, which means assuming it has mass, we can say that its acceleration is zero. So then we build off of that is if it's, say we take in its x direction. So if we say the acceleration in the x direction is zero, then we can say the time derivative of the velocity in the x direction is zero. By integrating both sides, we can find, so if we integrate this with respect to time, and the zero with respect to time. Okay, so what's important here is that when we're evaluating integrals in this way, which is really used in a lot of differential equations, which we're using the applied maths program in Leaving Cert, but a lot in mechanics we use differential equations to describe motion. So when we're solving these differential equations, we need initial conditions to really set down what we're talking about, to make sure that we're not in a completely abstract land, and it makes sense given the physical situation that we're trying to model. So in this case, we need to evaluate these two sides at a certain time, t, and a general time. So when we say a certain time, we usually like to say at the beginning of our experiment, or when the particle is released or begin measurement, or something along those lines. And we define that time at t equals 0. So that's why we can put it at the lower bound or the upper bound, but really for the sake of notation, we usually use the lower bound. And then we have to evaluate it at some general time t. So this allows us to turn it into a function of t, and it means that we're not just considering it at a certain point, but at any given point after time equals, or t equals 0. So when we have our derivative and integral cancelling out, so we'll have the velocity in the x direction evaluated at time equals 0 and t. And if we try to integrate 0, we'll get, again, 0. So we'll have 0 evaluated at 0 and t, which will go to 0 in general, because you can't evaluate 0 at t. It just would end up with 0 again. So then we get Vx at some point t minus Vx at some point 0 is equal to 0. So that means we have the velocity in the x direction as a function of t is the same as the velocity in the x direction at time equals 0. So what does this mean? This means that no matter what time we plug in here into our velocity function, it will be the exact same as the velocity of the particle when it starts moving, or whenever we start measuring it at time equals 0. So this means that our velocity is going to be constant no matter at what time. So we can say Vx here, but in reality, because our acceleration here is 0 for x, y, and z directions, this generalizes to all cases. So then if we were to take a similar approach up here, and we'll take Vx of t equal to Vx at naught, and this is the same as the position of t, so we'll call that, say, or x of t dotted, or the time derivative of it, and do the exact same thing as we did up here by integrating both sides with respect to t. So we get Vx naught dt, and yet again we'll have to evaluate it at the same initial conditions. So we have this at time equals 0 and 0, time equals t and t, because we want a function of t out of it. And yet again, the integral and the derivative will cancel out, and so we'll get or x as a function of t evaluated at t equals 0, t equals t, and we'll get Vx naught, which is a constant, times t, with t evaluated at t equals 0 and t. This is because if you integrate any constant function, you'll just get the integration variable back and then evaluate it at its limits. So this means we'll have or x as a function of t minus or x at naught is equal to Vx naught times t minus Vx naught times 0. This 0 will cancel out, so we can get rid of this. And so we'll get, and bringing or x naught over to the other side, we'll get or x sub t is equal to or x naught plus Vx naught t. And this is our final equation here. This is our equation that describes the position of the particle in the x direction at any given point, or at any given time t. So we can generalize this for all three spatial coordinates, and we'll have an exact position vector of where the particle, and just to be able to describe where the particle is at any given time. As long as we know or x naught, which is the initial distance from the origin to the particle at t equals 0, and Vx naught, which is the initial velocity of the particle. So this is our equation of motion for a particle at any given time. So we have the or vector is equal to or x naught plus Vx naught t, or y naught plus Vy naught t, and or z naught plus Vz naught t. So here's our position vector that describes the particle at any given point in time. Okay, so that was our simplest example, a particle with no forces acting on it whatsoever. So let's have a look at particles with force moving in the z direction alone. So that means we're able to keep our previous vector components of the x and y directions, but we'll need to deal with z by itself now. So again, we have our f equals ma, and if we just want to deal with the z direction, we can say the z component of f is equal to the mass times the z component of the acceleration, which means we have the force in the z direction over the mass is equal to the acceleration in the z direction, which is the same as saying the force in the z direction over the mass is equal to the time derivative of the velocity in the z direction. And then, like last time again, we're going to integrate both sides with respect to t and evaluate at t equals 0 the lower limits. Remember, it doesn't really matter what time equals 0 is. We just choose it pretty much arbitrarily. And then some upper bound of t, some general variable t, which will give us our function in terms of time. So evaluating this left-hand side, we get a constant integrated with respect to t will give us a t evaluated at t equals 0 and t equals t. And our right-hand side, again, the integral and derivative will cancel out, and will leave us with the velocity in the z direction as a function of t, because it is a function of t, evaluated at t equals 0 and t equals t. So the 0 on the left-hand side won't contribute anything, and so we'll be left with vz over m times t is equal to, or fz over m times t is equal to vz t minus vz naught. So moving this up again to the top of the board, we'll find that the velocity in the z direction as a function of time is equal to the initial velocity in the z direction, or vz naught, plus the force in the z direction over the mass times t. So now we have our expression for the velocity in the z direction as a function of t. Now we'll do what we did in the last example again, and we'll realize that this velocity is the same as saying the time derivative of the position of the particle in the z direction as a function of t is equal to vz naught plus fz over m times t. And yet again, we'll integrate both sides from 0 to t and from 0 to t. And this right-hand side, the first term of vz naught will be a constant again, and so we'll have vz naught, or vz naught t, plus, now we have fz over m, which is a constant, and our t, the integral of t with respect to t, is t squared over 2. So we'll have fz t squared over 2m, all evaluated at t equals 0 and t equals t. And on our left-hand side, again, we'll have our derivative and integral cancel out. And so we'll have or z as a function of t, evaluated at t equals 0, so initial conditions, and t equals t. So evaluating this out, we'll have or z of t minus or z naught, which is our initial conditions, is equal to vz naught t plus fz t squared over 2m. And our 0 will cancel out because, or will disappear because when t equals 0, vz naught t will be equal to 0, and when t equals to 0, fz t squared over 2m will also be equal to 0. So now, finally, we'll have that rz of t is equal to rz naught plus vz naught t plus fz t squared over 2m. And this is now our new equation for modeling the motion of the particle in the z direction. Okay, so yeah, if we have our fz not be some random force in the z direction, but if we consider it to be, for instance, gravity, which is about magnitude of about 9.8 meters per second squared, then when we have it working in the negative direction, we're going to write it in, or we're going to write az is equal to minus g, where g is this 9.8 meters per second squared. The reason we keep it in the negative direction generally is because it fits better with our intuition. We kind of think of the world with up being positive and down being negative, and so it fits better to keep g negative, or the acceleration negative. We could make it positive and redefine our axes if we so chose, but it makes no difference really, but it makes life a little bit simpler. So that means when we have our force in the z direction, it's the same as saying the mass is a in the z direction, which is minus mg, which means when we plug in this minus mg into our new equation here, we'll get that rz of t is equal to rz naught plus vz naught t minus gt squared over 2. And this is our general equation for describing the motion of a particle falling in the z direction. We now need to just know the initial distance above the Earth's surface and the initial velocity in either going up or down to be able to model our particle. Okay, so the final example we're going to go over with forces and dynamics is we're going to return to the simple harmonic motion. So we're going to say that a particle is moving along one axis and is being acted upon by a force. So this force is we get from Hooke's law. So we'll have the force in the x direction, but there's only a force in the x direction, is minus kx. So this minus k is called the spring constant, or this k rather is called the spring constant. It basically measures how springy a spring is. It's an experimental property of the spring itself. So mathematically, we'll just leave it as k and not have to worry about it anymore. So we then set this equal to ma, and we'll use dot notation, Newton's dot notation for this to make life a little bit simpler. So that means we'll say that m times x double dot, which is the second time derivative of x, is equal to minus kx. Now we'll divide both sides by m, and we'll see that the acceleration in the x direction is minus k over m times x, where x double dot is a function of t, and x is also a function of t. So this might look a little bit more daunting. We say that this is called a second order differential equation. So we can't really attack it in the same way that we did before. We need to kind of think of what would give solutions. But first, we'll have a kind of neat notational trick, and we'll let some omega equal k over m, which means we can rewrite x double dot of t equal to the square root of k over m. So I have minus omega squared x of t. This might start looking familiar because we had a similar idea when we were talking about circular motion, where the acceleration was minus omega squared times the position. And we'll see that this solution, or this equation, has general solutions. So the solution to this equation is x of t equal to a sine omega t plus b cosine omega t. So when we plug this back in, we'll get that x dot is equal to omega a cos omega t minus omega b sine omega t. We'll take the time derivative again, and we'll get that x double dot is minus omega squared a sine omega t minus omega squared b cos omega t. So this means we can group the minus omega squared together, and we'll get minus omega squared times a sine omega t plus b cosine omega t. And we'll notice that this is the same solution that we thought might be true. And so we can rewrite this as minus omega squared x. So here we have that x double dot is omega squared x, and we've proven therefore that this solution here, or this equation here, is a solution for this second order differential equation. Given that omega is then k over m, we can extrapolate and get our acceleration function back in terms of physical constants.